AI can write 1,000 lines of code while you pour your coffee, but pushing that raw, unchecked AI output straight to production is a recipe for a catastrophic system collapse. Casually prompting an AI and shipping whatever it spits out is called vibe coding. The problem is that human ad hoc quality assurance simply cannot keep up with this velocity. Reviewers skimming a pull request miss microscopic logical flaws hidden inside massive blocks of machine-generated text. When you let large language models, or LLMs, which are AI systems trained to predict the next token in a sequence, write code unconstrained, structural decay sets in. You get variable shadowing, where a local variable accidentally overrides a global one, and you get devastating security flaws like API keys hard-coded straight into your repositories. The antidote to this chaos is the Cody Master Framework. It operates as an architectural straitjacket. Instead of trusting the AI, it forces the code through a system of deterministic gates, requiring mathematical proof of safety before a single line is executed. Harnessing the raw speed of AI requires us to abandon human trust and hope. We have to replace them with an unforgiving, automated verification architecture. The core operational engine of this framework is the RARV loop: reason, act, reflect, verify. For a standard stateless LLM, reason and act are natural behaviors. If you ask a model to write a script, it will reason through the logic and act by generating the text. But reflect and verify are highly unnatural. An LLM does not inherently doubt its own output. To force an AI to critically examine its work and verify it against objective tests, we have to build rigid external scaffolding. This entire scaffolding is built on 4 distinct pillars: state persistence, strict test-driven development, multi-layer quality gates, and defense and depth security. True autonomous reliability does not come from empowering an AI. It comes from systematically constraining it. A stateless agent wakes up with amnesia every time you prompt it. Left to its own devices, it will push client code to your personal GitHub repository or hallucinate the wrong database credentials because it lacks persistent context across sessions. To solve this, we use an identity guard. This is an uncompromising hard lock, usually a JSON file named project identity, that explicitly maps out the allowed accounts and environments. The system must verify this file before any target environment is touched. Without state, you also face infinite debugging loops. A stateless agent will encounter an error, guess a fix, fail, and then immediately try the exact same hallucinated fix again because it has no memory of the previous failure. We break this loop using a working memory protocol. By routing structural errors into a persistent learnings file and orienting the AI with a continuity document at the start of every session, we give the model a searchable history of its own mistakes. But infinite memory creates its own problem: context window bloat. To manage token limits, we apply principles from the 19th century psychologist Hermann Ebbinghaus, who pioneered the experimental study of memory decay. This chart shows the Ebbinghaus forgetting curve, illustrating how quickly unreinforced information is lost over time. The framework mimics this by applying a 30-day auto-archive mechanism to the AI's memory notes. If an error pattern isn't encountered again, it decays and is removed from the active context window as soon as it crosses that threshold, saving crucial tokens. Mechanical identity checks and decaying JSON memory stores force a text generator to act as a context-aware, stateful entity. The second pillar relies on strict test-driven development, or TDD. The iron law here is the red-green refactor loop. If an AI writes implementation code before it writes a failing test, that code must be instantly deleted. If an AI writes a test after it writes the code, it will successfully engineer a test that perfectly validates its own hallucination. The test must come first to prove the intended behavior actually exists. When a test fails, the AI falls into the just one quick fix trap. It defaults to blind symptom guessing. When this happens, you often find yourself writing dependency injection, a technique to separate bloated, tangled code into independent modules, just to untangle the mess the AI made. When an agent fails a fix 3 consecutive times, we force it to stop guessing. We trigger a mathematical constraint called TRIZ, a structured problem-solving methodology designed to overcome cognitive deadlocks. This is the 9 windows matrix. It forces the AI to analyze the root cause of a bug by mapping it across 3 time periods and 3 levels of system complexity. By forcing the AI to populate this matrix, we map the persistent bug across temporal and spatial blind spots. It prevents the model from staring at the immediate symptom and forces it to trace the error back to its actual origin point. Enforcing rigorous test-first protocols and TRIZ matrices strips the AI of its ability to guess. It forces systematic engineering. The third pillar uses 4 core test layers: front-end safety, API, business logic, and internationalization, or I18N. But logical assertions in these layers mean nothing if the code itself is malformed. Raw syntax verification must always supersede logic tests. Look at the catastrophic I18N incident of March 2026 inside a front-end Next.js monolith. The engineering team had a false sense of security because 572 back-end tests passed perfectly during the deployment. Everything looked green. But the AI had mass-converted 600 translation strings in a single pass. In doing so, it introduced a flawed ternary operator nested inside a template literal. This created variable shadowing, effectively destroying the document object model, or DOM, the structural representation of the web page. The immediate consequence was an unrecoverable white screen for all users. The mechanical solution to bulk tasks like this is microbatching. We enforce a strict, non-negotiable threshold of exactly 30 strings per extraction batch. This prevents the AI's context window from overloading and corrupting the syntax. After every single 30-string batch, an 8-gate audit must drop like physical blast doors. These gates perform deep static analysis, parsing the JavaScript syntax and checking every delimiter. Gate 4 and Gate 5 specifically hunt for mismatched delimiters and structural HTML corruption hidden inside the JSON translation files. If the code hits Gate 5 and fails, the flow is severed instantly. Passing back-end logic tests means absolutely nothing if the fundamental syntax integrity isn't mechanically locked down at the parsing layer. The fourth pillar addresses the stark reality of AI development. Secrets leak at 5 distinct stages. They leak during write, commit, push, deploy, and runtime. To stop this, we deploy a 5-layer secret shield designed to intercept unauthorized data at every single vulnerable stage. Layers 1 and 2 begin by pre-prompting the LLM with hard safety rules, followed immediately by a utility called GitLeaks, which scans and intercepts any exposed keys right at the commit phase. Layers 3 and 4 enforce strict separation of environment variables and push the code through a rigorous 9-gate deploy pipeline. Finally, Layer 5 acts as the runtime guard, forcing 30 to 90-day cryptographic token lifecycle rotations to ensure that even if a key is intercepted, it quickly becomes useless. This entire deploy pipeline is sequential. If Gate 0, our secret hygiene check, detects a single anomaly, the deployment halts instantly. Developers often bypass these checks with a no-verify flag, thinking they will do it just this once. That exact moment is when a repository compromise occurs. Deployment security in the AI era cannot rely on human vigilance. It requires automated interceptors that remove trust entirely from the equation. When you step back and look at the fully connected Codemaster architecture, the identity guard, the memory protocols, the multi-layered tests, and the security shields, you see a complete system. True autonomous engineering is not achieved by giving a language model unlimited creative freedom. Safety is achieved by placing the AI inside an unforgiving, mathematically rigid straitjacket that ruthlessly filters its output. By enforcing continuous memory and multi-layered quality gates, we successfully replace blind hope with hard, verifiable mathematical evidence. The era of vibe coding is over. The future of senior engineering is no longer writing the syntax, but architecting the flawless constraints that govern the machine.